Hello, welcome to Material Science lecture. We are in our second week of lecture, and this is the last lesson that you need to know for this second week. So for this second module, so we are going to talk today about crystallographic direction and planes. By the end of this lecture, you should be able to understand the concept of lattice direction and plane. You should be able to determine the Miller indices of the plane and also the direction. And also you should be able to visualize and draw a plane when given its Miller indices. As for now, I'm pretty sure all of you have already known the concept of plastic deformation. So when the stress induced inside the materials is higher than its yield stress, what will happen is plastic deformation will happen. And during this plastic deformation, atoms will start move and it will slip along a certain direction or plane. So understanding lattice plane and direction is essential to explain why these atoms move in certain direction. And also some material properties such as electrical and thermal conductivity and elastic modulus can vary in different direction, especially for materials that we call as anisotropic. So an isotropic material is when the properties of materials is depending on the direction where you measure them. So we need to know how to annotate this plane and direction for us to talk about these properties of materials. So as I said, one example is if I want to describe the anisotropic properties of materials. For example, if I want to describe the electrical properties of graphene. So graphene is another allotrope of carbon where carbon atoms arrange themselves in a single layer of 2D honeycomb, as you can see here. So their electrical properties, the electrical transport, depends on what direction I measure them. So for example, if I measure them in this direction that you can see here and that direction there, I will get the same result. However, if I measure this electrical transport or electrical property in that other direction, I will obtain totally different results. So this is what we call as anisotropic materials. Something that we will talk a little bit more in our future model is about how atom slips when plastic deformation happens. So as you can see here, this is a unit cell of FCC. So when plastic deformation happens, the atoms will move in that direction, or also it can move in that direction along on top of that plane there. So why it happens like that, we will explain later. So again, in order for me to talk about this direction and plane in FCC, I need to know how to talk about plane and direction in crystal lattice. So Miller indices is the index that we use to describe the direction and planes in a unit cell, and they are the index method of describing the orientation of the plane or the set of plane within the lattice in relation to the unit cell. So before we start naming our plane and direction, we need to identify the coordinate of each lattice point in our unit cell. So in order for us to do that, I prepared some simple exercise for us to do it together in order for us to identify the location of each of these lattice point in its unit cell. So if I choose O here as my origin, the coordinate for A should be 1, 0, 0. The coordinate of B here should be 0, 1, 0. And so on. For C, the coordinate should be 0, 0, 1. And the coordinate for D is 1, 1, 1. And so on. And I have this odd lattice point here that I indicate as H, the coordinate for H is half, 1, and half into relation to this unit cell. All right, so that is that. Now that we know the position or the coordinate of each of this lattice point, and we're good to go in indexing our plane and also our direction. So I will start with how to index direction first. So how we use Miller indices to index direction. So direction in a unit cell is a line between 2 points, and it is a vector. So let's say I have this unit cell here, and it is cubic unit cell, and they all have the same lattice constant. And now I'm interested with this direction. So let's say I have a material properties in that direction that I am interested with, and how am I going to start indexing this direction? So direction can be denoted with Miller indices HKL in a square bracket. So to start indexing this, I need to get 2 points that lie in the direction, in this direction. So say I will use the tail coordinate is 1 point, so I denote it as 0, as O, and I also have F here as the head of the vector, and that's the 2 point that I have that lie in that direction. So now I need to find the coordinates of these 2 points. So if I set up my X, Y, Z coordinate system as what you see here, where I have X direction, Y direction, and Z direction, as what you can see in the slides. So now I can find the coordinates of my tail. So that's the coordinates of the tail. So the tail is located at the origin of that coordinate system. So now I need to find the coordinate of the head of the point F here. So the coordinate of point F is half direction to half unit in X direction and half unit in Y direction and 1 unit in Z direction. So the coordinate for the head is half, half, and 1. So now to get the Miller indices, I need to subtract that head with the tail. So I need to subtract the tail from the head. So if I do that subtraction, I will get half, half, and 1. So now my number is in fraction. So I need to clear this fraction. So to clear this fraction, I will need to times this whole thing. So when you do the subtraction, what you will get is half, half, and 1. So you need to subtract the head, the tail from the head. And now it is in fraction. So I need to clear this fraction. So I will need to times everything with 2. So what I will get is 1, 1, 2. So after you clear the fraction, you write this integer in square bracket like this, what I show you, and that is the Miller indices for this direction. So if, let's say, when you do the subtraction, you get a negative integer, this will be indicated in the square bracket with bar over the integer. So we'll do some more exercise so that you will get familiar on how to index this direction. All right, so I have several directions here that I would like you to try, but I will do 1 or 2 with you together. And after you try it, if you are curious and you want to know if you get the right answer, you can always come and contact me. So let's say we want to solve, we have already solved the vector OF, now we want to solve OC, right? So I have this direction OC here that I'm interested and I want to index them. So the first step that you need to do is to find 2 points in that direction. So the easiest point is to get the tail and also the head. So for this one, the tail is 0, 0, 0. The coordinate of the tail is 0, 0, 0, and the coordinate of C is 1, 1, 1. So it's 1 unit in X direction, 1 unit in Y direction, and 1 unit in Z direction. So what you need to do is now to subtract the tail from the head. So the head is 1, 1, 1. The tail is 0, 0, 0. So subtract them, 1, 1, 1. And since there are no fraction, you can straight away put it in the square bracket, and that is the Miller indices for that particular direction. So that's 1, 1, 1. So another one that I would like to do is this CB, direction CB. So I will erase the one we just did. So we have some space here. So again, with this, what you need to do is to find the coordinate of the 2 points. So here the head is B at that point B, and we have the tail at that point C. So that point B, that point C, the tail, the coordinate is 1, 1, 1. And the coordinate for B is 1, 1, and 0. So that's the coordinate for these 2 points. So to get the Miller indices is to subtract the tail from the head. So the head is 1, 1, 0. The tail is 1, 1, 1. So you subtract them, you get 0, 0, negative 1. And as I said, in indexing with Miller indices, when you have negative integer, that negative integer will be denoted in the square bracket as bar 1, bar on top of that integer. All right, so you have 0, 0, bar 1. So that is the Miller indices for this particular direction, the vector CB. But there's another way of you to get that vector CB. So if I erase that again, what other thing that we can do? Because we know that this cubic unit cell is repeating, so it's filling up the whole volume of that material. So our origin can be anywhere. We can set up our XYZ coordinate everywhere. So it can be here. So I can say that is my XYZ direction. So that's my Z, and this is my Y, and this is my X. So I say that is my new coordinate system. So that's my X, Y, and Z coordinate system. So now the origin is at C here. So the new origin is at that C point. So that tail is now at a coordinate of 0, 0, 0. And the head here is at 0, 0, negative 1. So when I subtract them, so I have the head here as 0, 0, negative 1, and I have the tail as 0, 0, 0. So when I subtract them, I get 0, 0, negative 1. So they are the same. So when you put it in Miller indices in the square bracket as Miller indices, it's 0, 0, bar 1. So that's another way on how to find the direction. All right, so now what if in the exam you were given the Miller index instead of you were asked to get the Miller indices? So how are you going to draw these Miller indices? You are asked to draw it in a unit cell. So what you need to do first in this case is to set up your XYZ coordinate system. So here I've set it up as this, where I have this O here as my origin. So if you were asked to draw, your tail always should be at that origin there. So that is going to be your tail. So if I have, I'm going to draw this 250, Miller index 250, the direction of this in this unit cell. So this is an example, and you can try by yourself all the other index. All right, so the tail of this index will be at that 0, 0, 0 at that coordinate. And then to get the coordinate of the head, I need to divide so that the largest index in this Miller index will be equal to 1. So this is to get the head of the vector. So when I do that division, I will get 2/5, 1, and 0. So this will be our coordinate for the head. So it is 2/5 in the direction of X, and then 1 in the direction of Y, and there's no direction. And this head will be on the plane of X and Y. And then what I need to do next is just to connect the head and the tail together. So that is the direction that denoted by this Miller index of 250. So that's how you draw when you are given the index instead. Number of crystallographic direction can also be symmetrically equivalent. So a set of direction related by symmetry operation of the lattice or the crystal structure is called or as a family of direction. So instead of the square bracket, now you can represent all these directions, and you can see in this diagram here. So there are 6 directions here. They are all related by the symmetry of the lattice structure. So they can be represented as HKL in the angle bracket instead of the square bracket. So you can actually choose any number here. So you can choose 0, 1, 0. And if you put it in the angle bracket, I know what you mean is all these 6 other directions. So here I choose 1, 0, 0 in the angle bracket. So as soon as I see that, I know what you mean is 6 directions that are related to this one direction. So that they are all related by symmetry. Right, so now let's go on and index our plane, so our crystal plane. So how do we index crystal plane? Is using Miller indices HKL, but now in a regular bracket. So if you put it in a regular bracket, straight away I will know that what you mean is the crystal plane. So say I have this crystal structure, and the unit cell of this crystal structure is this simple cubic unit cell. And I want to identify this plane. So what do I need to do first is to set up my XYZ coordinate system and set up where is my origins going to be located. So to index this plane, is the first thing you need to do is to identify the intercept of the plane in each of the axes. So at x-axis, it intercepts at half. So you must by now know that this is 1 unit. So in this unit cell, this is 1 unit, and that's 1 unit. So it doesn't mean that it's 1 centimeter and 1 nanometer. It doesn't mean that. It's 1 unit. For that unit cell, that lattice constant is 1 unit. So the plane is the plane intercept at x-axis at half, and 1 in y-axis, and it intercepts at z-axis at half. So we have 1 at half, 1, and half. So that's not our Miller indices yet. Taking reciprocal of this intercept will give us the Miller indices. When you reciprocate them and put them in the the bracket, the regular bracket, and that is the identity, which is the Miller indices for this particular plane, crystal plane. So that is how you index the crystal plane in a unit cell. If the intercept are 1 over h on the x-axis, 1 over k on the y-axis, and 1 over l in the z-axis, the Miller indices are HKL. Or if the resulting indices contain fraction, multiply throughout to give the integer value of h, k, and l. So for example, if you have come up with the intercept as 1 over 2, then in the x direction and y direction you have 1 over 3, and suddenly your z-axis is 2 over 3. So this is what you get. Get the reciprocal, you will get 2, 3, and 3 over 2. And now you cannot have fraction in your Miller indices, so you multiply throughout. So you will get 4, 6, and 3. And this is your, so that should be your Miller indices. All right, so what happens if we have a lattice plane, a crystal plane that does not intercept in all 3 axes? So for example, we have this crystal plane and we want to annotate them with Miller indices. How do we do it? So this plane intercept at x-axis at 1, and it intercept at y-axis at half, but it doesn't intercept at z-axis. So what do we do with the index L? So we have h, we have k, but we don't have L because it doesn't intercept in z-axis. So this plane can be said to intercept the z-axis at infinity. So in this case, we can use 0 for the Miller index of this z-axis. So the L index, you can put it as 0. Right, so how about negative index? So let's say I have this unit cell here and I'm interested with that plane, the crystal plane there, and I want to index them. As soon as if you find out that it is hard for you to start indexing them, to get the intercept, move your origin, move your XYZ coordinate system. So it's the same as what I explained before with the direction. You can move them anywhere because you have to remember that unit cell is stacking one top of each other. So it can be origin of this unit cell or this unit cell or this unit cell. So it doesn't matter. Move it around. You are free to move it around because the unit cell is filling the whole volume. So with this one, to index this plane, it will be useful to use different corner of the unit cell as the point of reference. So now I'm going to move that origin to this new origin. So my XYZ coordinate system is now looking like this. So from here, I can find the intercept in each of the axes. So I can see that it goes along x direction, z direction to intercept at half, and also with x, it goes along x direction to intercept at 1, and it goes backward in y direction to intercept at -1. So now I get all the intercept. So my intercept is 1, -1, and also half. So reciprocate them and get your Miller indices. So I have 1, 1, and 2. And this is -1. So with the negative, instead of using minus system, we use over bar to denote the negative index. So this is my Miller indices for this crystal plane. Now, how about if I give you the Miller indices for the plane and I want you to draw it? So in exam, you would be given this kind of questions as well. So let's draw together the plane, crystal plane of 3, 1, 2. So I want to draw this in this cubic unit cell. So it is necessary for me to choose the correct point of reference for this to start drawing this plane. So I will choose that O as my point origin and this X, Y, Z coordinate system as my coordinate system. So what you need to do first is to take reciprocal of each of the index, the H, the K, the L, and this will represent the X, Y, and Z direction in your cubic unit cell. So I can see if I take reciprocal of the 3 for the H index, it will be 1/3. So 1/3 is where that plane is going to intercept in the X axis. And 1, the reciprocal of 1 for K is 1. So that is where it's going to intercept in the Y plane axis. So if I take reciprocal of 2, it's going to be half. So that half is the intercept in the Y and the Z axis. So the last thing you need to do is to join this point together and form your plane. So that is how you draw when you are given the index, and you will be given this kind of question. So in your tutorial, you can see some of this question appear in your tutorial. Let's do another one. So I have this Miller index. I want to draw the crystal plane. So definitely we can see bar 1, bar 2, and 1 here. So this is negative index. So I have to choose the most convenient point of reference. So if you choose 0 here, the O here as your point of reference, you're going to be in trouble. So we can see in Y direction, it is in Y axis, it is negative. X direction is also negative, and we have positive in the Z direction. So the most convenient point would be here, as I show you in this diagram here. So here now that you can start locate your intercept. So if you take reciprocal of H, K, and L, you get this as your intercept. It will intercept at 1, -1 for X axis, half, -half in Y axis, and 1 in Z axis. And then combine them all together, that is your crystal plane. And again, how about this one? So this one is bar 1, 0, and 1. So you know that one of the axes, which is X axis, this plane would not intercept in that axis. And it will intercept at -X instead of X. So we need to move our point of reference again. So for this, what is the most convenient point of reference? So the most convenient point of reference would be there, because it's going to be giving you a negative index for the X. So I will start by locating where is my intercept. So it will intercept at 1 for X direction, and also it will intercept at -1 for X axis, and it will intercept at 1 for the Z axis, and it won't intercept at Y axis at all. So I have located this with the green point here. So this is where my plane is going to intercept, and that is how it's going to look like. So practice with the one that I gave you in your tutorial. Do a lot of them and find some other plane that you want to identify and keep on practicing. So the same with direction, plane also related by symmetry. So take for example this plane here. So this plane is a 1, 0, 0 plane in a unit soil of primitive cubic lattice. So we can change the orientation of the axis, and now this plane with this axis, it is 0, 1, 0 plane. And again, if we rotate this again, the axis is rotating again. It is now giving us 0, 0, 1 plane. So they are all related by symmetry. So we can also have bar 1, 0, 0 plane, and they are all going to be related by symmetry. So we can do this because these planes are related by symmetry of the lattice. So this is now what we call as the family of planes. As you can see here, all of these planes are related by symmetry, and we can use square bracket, and no, we can use curly brackets to represent these planes. So if you indicate 1, 0, 0 in a curly bracket, I know what you mean is all these 6 planes, and they are all related by the symmetry of the crystal lattice. So we get to the end of our lecture. So this is the last lecture for this week. So in summary, throughout this lesson that you get from me in this video, by now you should know that Miller indices are the convention used to label lattice plane and direction. And this mathematical description will allow us to define accurately planes within a crystal, and quantitatively will analyze many problems in material science. All right, so that's about it. Thanks for taking your time watching this video. Go and try do your tutorial. By now you should be able to complete them, and we will discuss this next week. Thank you very much.